Hello students, this video is the first part of the Chapter 7 video. Chapter 7 is entitled The Quantum Mechanical Model of the Atom. So as you are taking notes, that might be a good title for this section of your notes. So let's talk about what we're going to be covering in Chapter 7. First of all, the quantum mechanical model. What in the world is a model? So a model is simply a mental picture. Let me get my better black marker here. A mental picture that scientists make of things they can't directly observe. The idea here is that no one can actually and has actually seen an atom, certainly not the inside of an atom, but we have data, experiments that will give us a clue as to what's going on inside of an atom. So Chapter 7 is all about giving us a good picture of what does an atom look like on the inside. If you remember from one of the earlier chapters, Ernst Rutherford's experiment showed us that the atom has a nucleus, and that's where all the positive charge is. But that whole electron cloud part of the atom, what's going on the rest of the atom besides the nucleus, that's really what the quantum mechanical model is really going to be trying to address. So what we can't see is the inside of an atom, but the model is the current one is called the quantum mechanical model. So let me go and give you a couple bullet points. So the quantum mechanical model is the current model of the atom. In other words, the one that scientists accept based on the experiments that we have to this point. Models constantly change because it's not perfect. It's not like a direct observation where you say, you know, the graph says green or the temperature rose from this to that. It's just the best that we can do with things that we can't see. So models constantly change. This is our current model of the atom. We are also going to be learning in this chapter a very significant precursor, and that's called the Bohr model. Which is a precursor model. This is the one that used to be accepted. And actually, some people, I can tell based on drawings that they've used and things like that, some people actually still maybe aren't under the impression that this Bohr model is the current model, and that's one thing I'm trying to kind of unwind with this. So we will be learning about the Bohr model, which is our precursor model, to the current model, which is quantum mechanical model. And then lastly, before we get into it here, the key principle behind the quantum mechanical model is this. Electrons. Because once again, we're really trying to figure out what's going on with the electron cloud in an atom. We already know about the nucleus, that's where the protons are. But what about that whole rest of the space of an atom? What's happening there? The key principle behind the quantum mechanical model is that electrons have both a particle and a wave nature. All right, so there's some physics going on here. Particle and wave nature. Maybe you've heard about it, the concept of wave-particle duality before. This is something that electrons are known to have. And what we also know is that light also has this concept of a dual nature, particle and a wave nature. So both electrons and light have something very much in common, wave-particle duality. So we spend a lot of time in Chapter 7 trying to understand what in the world is wave-particle duality. And then once we learn about it in the concept of light, we can kind of apply it to electrons. And that, believe it or not, leads us to the quantum mechanical model. Just to, in case you have some background in this, Quantum mechanical model is what we are using when you write electron configurations such as 1s2, 2s2, 2p6. All of that is quantum mechanical model of the atom. Okay, the idea of s orbitals, p orbitals. If you don't know anything about that, you will soon by the end of this chapter. But that's what we're talking about when we talk about the quantum mechanical model. The Bohr model had nothing with S and P or D or anything like that. So let's go ahead and get into this part here, kind of laying the groundwork for what in the world is wave-particle duality? What are we talking about? But we're going to start at it from the point of view of light, because frankly, that's where scientists started at it as well. Scientists learned a lot about light and then applied much of it to electrons. All right, so let's start with examining light. Like I said, a lot of this kind of feels like physics, but physics and chemistry intersect here, so that's kind of a neat thing. All right, so let's title this next section light. All right, so first of all, what is light? Light, I mean, you know it, it's coming from light bulbs, coming from the sun, but it is something with a definition. It is a defined thing. So what is light? Light is a form of energy. So light can be measured in joules. It's a form of energy, which is embodied in oscillating, and I'll define that word in just a minute, electric and magnetic fields. And therefore, light is also known as, AKA, it's also known as electromagnetic radiation. That is a synonym for light. So you can see the words electromagnetic, that's the oscillating electric and magnetic fields. So when we use the term electromagnetic radiation, we're also talking about light. They're synonymous. Let's talk about what's oscillating. Oscillating just means composed of up and down repeats. If something oscillates, like the piston on a motor, it goes up and down repeatedly. And then what is an electric and a magnetic field? Let's go ahead and define these two things as well. An electric field is any space, any area in which an electrically charged particle experiences a force. Okay, so we can certainly understand this. An electrically charged particle, we have learned about actually 3 types of electrically charged particles. We've learned about protons, which as we know have positive charges. We've learned about electrons, which as we know have negative charges. And we've also learned about ions. Ions are also electrically charged particles. They're just, a lot bigger. But any ion would also be an electrically charged particle. If you are talking about an electric field, you're talking about any area where these are going to feel something, either an attractive or a repulsive force, which we have already given you the vocab term for that. These are called electrostatic forces. So for instance, let me give you a for instance. I think for instance is e.g. The area around a nucleus would be an example of an electric field. Because if you have a nucleus of an atom, we know that there is a positive charge there, because that's where protons are. If any one of these charged particles enters this area around that nucleus, so say the proton comes in and enters this area, he's going to feel a force. For him, it'll be a repulsive force because it's like charges. An electron, if he enters this area, he'll feel an attractive force. So that's just an example of what an electric field is. It's actually not too hard to understand. A magnetic field is very similar. It's any space in which a magnetic particle experiences a force. So first off, we just want to reiterate that being electrically charged and being magnetic is not the same thing. We haven't talked a lot about magnetism. It's a bit more in the realm of physics than it is, it does affect chemistry, but for our class, we're just going to kind of leave that alone, knowing that they're two different things. But let's talk about what a magnetic field would be. Something like your refrigerator. Okay, here's your refrigerator. The area around your refrigerator would be a magnetic field, because a magnetic particle, like a magnet, as it approaches that area, will experience a force. If it's a magnet, it'll experience an attractive force to your refrigerator because of the metal. So that's just an example of what a magnetic field is. Now, this picture, obviously I don't have my slides for you. I just printed out the slides that I thought were kind of helpful. These are all from the textbook. But this is what a picture of light is. You can see that, first of all, light is also called electromagnetic radiation. You can see that you have two components. You have the electric field component, right, this is hard, okay, right there, and you have the magnetic field component right there, and they oscillate, they go up and down, and they also are perpendicular to each other. That's not super important for us to focus on, but they are. And then also, the next thing I want to put on the board about light is that light moves. You can see direction of travel right there. Okay, so light is something that travels. So let me get some space on my board. So we have what light is. It's electromagnetic radiation. It's a form of energy, can be measured in joules. Let's go ahead and give you a couple things about light. Light travels very fast. Most people know that. Very, very fast. Much faster than sound, which is why the whole concept of seeing the lightning before you hear the thunder, all of that is just the speed of light. Travels very fast at a constant speed, actually. Let's talk about that. At a constant speed. It's always the same speed. And the speed of light is something that we abbreviate, and you're going to use this in equations in just a little bit, with a little lowercase letter c. So lowercase letter c stands for the speed of light. It's a constant in the universe. And I want you to know its value. The speed of light is equal to 3.00 times 10 to the positive 8. That's a really big number. Meters per second. It's a speed, so we measure it in distance per unit time. And meters and seconds are the SI units, so that's why the speed of light is in this unit. So 3.00 times 10 to the 8th meters per second. We want to kind of know that that's a constant. All right, so light travels very, very fast. And then the last thing about light is that light displays this very unique and kind of perplexing characteristic called wave-particle duality. And duality just means two things at the same time, or both things. So the idea here is this. Sometimes light is best understood as a wave, okay? And we'll talk about that in just a little bit. And then sometimes, so let me draw a wave. And we'll draw a better wave in just a minute. But sometimes, which moves, but sometimes light is best described as a particle. And what we will learn is that these particles are referred to as photons. Okay, so it's kind of both. And it almost depends on the type of experiment as to which better describes light. And like I said in my introduction, at the end of the day, the reason this is important into quantum mechanical model of the atom is that electrons have this very unique property as well. Sometimes they're best thought of as particles, and sometimes they're best thought of as waves. And that kind of is the whole basis of quantum mechanics. All right, so let us proceed into the next part of this lecture, which is how do we know that light is a wave? Okay, so all of this is, you know, light helps us to see, we experience light, we turn on the lights, you can see, but what is light? What if you could, you know, scientists are trying to understand what is it, what does it look like, or how does it act, that kind of thing. That is really what we're getting into with this next part of this chapter. So let's examine the wave nature of light. Let's examine the wave nature of light. And really what we're kind of asking is this question. Really asking this question. How do we know that light is a wave? It's not something like, I mean, you can look at water and you can see water waves. So it's not so much of a question with water, you can visualize it. With light, it's a lot harder. So there have been experiments, and we're going to actually learn them in this lecture, that actually prove that light is a wave. It's not just a conjecture. We're actually going to show that light is a wave. So how do we know? Let's kind of build this foundation here. How do we know that light is a wave? Now, the key here is this. Here's the key point. What we call a wave is a physics phenomenon. There are lots of types of waves, okay? We have water acts as a wave. We have sound acting like a wave. And what we're about to learn is that light also acts like a wave. But waves are not unique to light. In fact, many of the things that we learn about waves, and even, I got blurry for a minute, even today, they study by studying water. How does water behave? And then they can apply this physics, you know, the physics principles to all types of waves. So a wave is a very general physics phenomenon. And like I said, what we're going to discover is that, maybe I didn't say, but what we're going to discover is that waves behave certain ways, okay? And I'm going to lay this out on the board. And when we find out that light does the same thing, it's like a logical conclusion that light must be a wave. Kind of like if it acts like a duck, walks like a duck, quacks like a duck, it's a duck, that type of concept. We learn about what waves do, then we see light doing the same thing, and therefore light must be a wave. That's kind of the conclusion that scientists have drawn about light in terms of its wave nature. Hopefully that makes sense. So let's talk about waves in general. So let's go ahead for this part of the discussion. Let's go ahead and draw an imaginary horizontal line, because this will help us draw a nice wave. So draw like an imaginary horizontal line. And let's go ahead and draw a wave, and we'll label some parts of a wave. And like I said, this is a physics phenomenon. This could apply to water, this could apply to light, this could apply to sound. So when you draw a wave, you want to go up, and then when you go down, try to make it the same kind of height. And then we'll just end right there. That's a pretty decent wave. All right, so when it comes to a wave, you can label certain parts of a wave. We'll start with this part here of the wave. Okay, so the distance from this is an imaginary line here. It's just the midline to the wave. The distance from the midline to the top of the wave. By the way, actually, you know what? Let's label this. The top of the wave is called the crest. That is the top of the wave right there, the crest. And and you know what? Let's just go ahead and label this. The bottom of a wave is called the trough. All right, so I can use a little bit of vocabulary here. The distance from the midline to the crest, or frankly, the midline to the trough, because it's going to be the same. A wave is going to have this pattern where that distance is going to be the same, okay, the whole way along. That is called the amplitude, AMP, but maybe write the word amplitude. All right, so let me spell it right here. That's how you would spell it, but let me just label it AMP, the amplitude. So that's one thing that you can measure about a wave. Then another thing that you can measure about a wave is the distance from crest to the very next crest. So here's the next crest over here. And this distance here from crest, let me just do a dotted line here, to the next crest is called the wavelength. The wavelength. Now, when it comes to amplitude, we're not going to be doing anything. That's more for us, just a concept. We're not going to be doing anything with measurements or units or anything like that. However, with wavelength, you will be doing some calculations. So let me go ahead and give you the unit that wavelength is going to be measured in. Now, it is like any other thing, a length. You can see wavelength. So it's going to be measured in meters. Any length or distance in the SI system is measured in meters. However, because many forms of light have very short wavelengths, you will see it measured more in nanometers, in micrometers, smaller, but it's still a form of a meter. It's just a metric with a metric prefix on it. But meters or some form of meters. You'll see a lot of nanometers. So that's the wavelength. Technically, it doesn't have to be measured from crest to crest. You actually could measure it really from any two analogous points on the wave. So I could have actually measured the wavelength from like this point to this point as well, because this is an analogous point. So the wavelength is essentially, if you wanted a good definition, it's the distance between any two analogous, that means kind of similar, points on the wave. And most people just do crest to crest, but it really can be any two similar points. It'll be the same distance. Alrighty, so let's go ahead and let me write wavelength here. Amplitude and wavelength. Now these two different things that you can measure actually tell you two different things about the wave. Amplitude is related to the intensity or brightness. Now I'm going to kind of talk just about a light wave here. Into the intensity or brightness of light. All right, so if you have like a dimmer switch in your whatever room, you are changing the brightness of the light. You're not changing the color or anything like that. You're just changing the brightness. That's related to the amplitude, how high the amplitude is. And as you might imagine, the higher the amplitude, the higher the intensity or the brightness of the light. So very high amplitude would be very intense light. Wavelength is actually going to be related to something else. Wavelength is related to color, at least for the type of light we call visible light. We will talk about other types of light soon. But when you change the wavelength, or when you have different wavelengths, you're actually going to get different colors. Now, I don't have a color printer at home, but I did have a slide here. And by the way, this is just figure 7.2 from your book, but it's a helpful figure, so I want to show it here. Let's start here on this side here. Let's start on the right. You can see where it says different amplitudes, different brightness. Dim light would have a small amplitude as opposed to bright light, which would have a large amplitude. And then over here on this side here, you can't see it from my non-color printer, but this one is red. That is supposed to be yellow, and that is supposed to be blue or maybe violet. I'm not sure. But anyhow, what you can see is that these waves all have the exact amplitude, same amplitude. If you look at the amplitude of the waves, they're all the same. What's different about them is wavelength. This one here has the longest wavelength. And we actually, and you'll learn this soon, in the colors, red is actually the one with the longest wavelength. And then this one down here, of the three that are pictured, has the shortest wavelength. You can see what they're trying to measure right there, wavelength. And that is, I believe it's supposed to be violet light, because that of the colors is the shortest wavelength. Now, let me stay here for a minute holding this up here. Both wavelengths, but also amplitude are related to the energy of a wave. Let me put this down for a minute and add something to our notes here. Both amplitude are related, both of these, amplitude and wavelengths, are related to energy, to the energy, or the amount of energy in the light, to the energy of the wave. Okay. And it's kind of common sense, actually. You can probably figure out where we're going with this here. Let's start on the amplitude side here. If you had to think about it, which wave do you think is more energetic? Small amplitude or high amplitude? And just think about which one you would rather swim in. This one's going to take a lot, or maybe you'd rather swim in this one, but this one's going to be the more energetic wave if it was water. So what we're essentially saying is the higher the amplitude, the higher the energy. And then over here on the color side, which one of these three is the highest energy wave? And using your common sense, once again, even thinking about which one would be most difficult to swim in, this one down here is going to have the highest energy because it has the smallest wavelength. So right there, we can draw another thing here. The higher the energy, so we're looking at relationships, the higher the amplitude, but the shorter. Oh, I just realized I forgot to give you the letter for wavelength. Let me go ahead and give it to you now. That little letter right there, it's called the Greek letter lambda. This is an abbreviation that we use for wavelength. Okay, to learn how to draw it, you're going to see it quite a lot. That's the Greek letter lambda, and it's what we use to abbreviate the word wavelength. I'm assuming it's the Greek equivalent of the letter L, which we use for length. But anyhow, coming back to here, the higher the energy of the wave, the shorter your wavelength. Okay, so you can see some relationships here. Energy and amplitude are directly proportional. Energy and wavelength are inversely proportional. Coming back to proportionalities, things that we learned in chapter 5. All right, so that's a little bit of kind of the geography of a wave. But there is one more thing about waves that we can learn, or that we can measure. Another characteristic of waves, and that is called frequency. So frequency. Okay, frequency is a really important concept as well in this chapter. First of all, it also has a Greek letter. Lambda is wavelength. Amplitude doesn't really get a Greek letter. Frequency is this letter here, and it's actually the Greek letter nu, N-U, but it looks kind of like a lowercase v, but almost like with some curve to it. It's not the same thing as straight lowercase v. Straight lowercase v in math and science is velocity. Greek looks like a v refers to frequency. And frequency, what is frequency? Frequency is the number of cycles. And what do we mean by a cycle? One cycle of a wave essentially is just this. Once up, once down. Once you've done one of those, you've completed one cycle. So that's a cycle. The number of cycles that pass through a stationary point. Stationary means not moving, like a stable point. A stationary point it's per unit time, but it's pretty much per second. That's the unit time that we use, per second. So to understand frequency, this slide is also what I usually use here. If you picture, let's go to this side here. All right, so picture understanding that waves are moving. Okay, light waves are, well, all waves move, but light waves are moving. So let's just say they're moving this way. They're all going to move the exact same speed. Okay, the speed of light, 3 times 10 to the 8th meters per second. But if I was to just kind of force am I making sense here? Yeah. If I was to force just a stationary point right there, like the end of the figure for all of them, and I had a timer and I let all of them go for 1 second, like 1 Mississippi, which one of them would have, oops, which one of them would have the most cycles that were able to pass through that point? And hopefully you can see that the ones that have the shortest wavelength would have the most of these that we're able to go through, because it doesn't take as long, you know, because their wavelengths are so small. So that's what frequency is. And there is a couple things I want to say about frequency. So frequency has units of, there's actually 3 units that are used for frequency. One of the units is cycles per second. Okay, so that's one of the units that you could use for frequency. Another one, and frankly the one that's the most common, is just, it's called s to the -1. When you have a -1 as your exponent, you're essentially just saying that that thing is in a denominator. So it's basically the same as this unit without the word cycles. It's just per second. It's just this part of it. And that's actually the most common unit that you will see for frequency, s to the -1. It just means per second. And then the last is the hertz, which is H, capital H, lowercase z. These units are all the exact same thing. They are all interchangeable, kind of like centimeters cubed and milliliter, how you can literally place one with the other. These are all the same. It's the same thing. If you have something that's written as hertz and you don't want to see it as hertz because you're more familiar with this one, you literally can replace it as s to the -1. So they're all interchangeable. All right, and then let's also put another thing up about frequency. I will just put it right here. So that's bullet point number 1. Let me give you another bullet point here. As wavelength decreases, frequency increases. That's what I was just talking about with that slide. As you have a shorter wavelength, you will have a higher frequency. And so what type of relationship is that? Once again, inversely proportional. Small wavelengths, high frequencies, and vice versa. If you have a long wavelength, you will have a low frequency. So the larger your wavelength, the lower your frequency. Now, our first equation, where you can do a little bit of math. Wavelength, so it's not just a relationship. It is actually an equation that you'll be using to relate frequency to wavelength. Let me go ahead and erase this here. This is a really important equation in this chapter, but luckily it's very simple. C equals lambda, which of course means wavelength, times nu, which is frequency. You don't need to use the Greek letters, just know what they look like. So this is a relationship that you'll want to know. C stands for the speed of light, and of course that's wavelength, and that is frequency. So let us go ahead and actually the inverse relationship is kind of obvious here too, because if the speed of light is a constant, it always has to be the same number. The bigger your numbers here, so like the longer your wavelengths, the smaller your numbers will have to be here. So the lower the frequency. So even that inverse relationship is kind of evident when you look at this equation. So let me go ahead and show you a practice question that you would have to use this equation. Just it's kind of best explained with some practice questions. Could we calculate the frequency of, let's say, a red light that has a wavelength of, let's go 575 nanometers. Okay, so in this question, I have given you a wavelength. And the wavelength is 575 nanometers. Once again, you can see it's measured in meters, but with a prefix because it's really, really small, so nanometers. So we have the wavelength and we are trying to calculate frequency. So what I always would do is just write that equation on my paper, and I would rearrange it for frequency because that's what I'm trying to solve for, frequency. So if you want to rearrange that for frequency, you would have to divide both sides by wavelengths. and that will isolate frequency. So frequency will equal C over wavelength. Now, C is a constant, 3.00 times 10 to the 8th, and it's really important to always put in your units, meters per second, meters per second. And then we are going to divide by the wavelength. Now, here's where we just have to kind of be smart about it. If you put in 575 nanometers, you are not going to be able to cancel that meter unit. You've got to be able to cancel that meter unit so that you have the frequency in an acceptable unit, which is s to the minus 1. So we're going to have to turn that into regular meters. So 575 nanometers, just doing it like we've always been doing it. In every 1 meter, there are 10 to the 9th nanometers. Remembering that nano is 10 to the 9th, and then just going to your calculator and doing 575 divided by 10 to the 9th, and you're going to get 5.75 times 10 to the negative 7th, I believe. Yeah, 10 to the negative 7th meters. And that is what you would put in for wavelength. You can see that meters will nicely cancel now. And now when you go to your calculator, make sure that you enter it correctly. You might need to use parentheses to make sure you're dividing by this whole thing, especially these numbers that have scientific notation down here. If I'm dividing by them, I put the whole thing in parentheses. So 3 times 10 to the 8th divided by that wavelength should give you a frequency of 5.20. Let's do sig figs. So both of these had 3. So 5.22 times 10 to the 14th. And look at the unit. It's an S, but it's in a denominator. So we write s to the minus 1, which is one of the acceptable units for frequency. And actually, I just leave it as that. That's a good unit. You can see it's a really huge number, but it makes sense because light is really small, and that's a really tiny wavelength, and it moves really, really fast. So you're going to have a lot of cycles go through per second. So that makes perfect sense. So that's how we would calculate frequency from wavelength. And hopefully you can see that in this very same way, if you're given frequency, you can get wavelength, just always through this speed of light equation. So it's once you know one, you can always know the other. That's a good thing to remember about this chapter. Anytime you know frequency, you can get wavelength. And anytime you know wavelength, you can get frequency, because it's all related through this equation. All right, so that's one type of practice question that you'll see in your homeworks. All right. Now, the next part of the lecture that I'd like to talk about is the electromagnetic spectrum. This is another figure from your book. There's a lot of numbers in it. Let me see what figure it is. 7.5. And I do want you to have parts of this committed to memory, the electromagnetic spectrum. Okay, so let me talk about what that is. I'm going to basically put it up on the board. So when we say the electromagnetic spectrum, what are we referring to? Okay, let me just put this in regular person language here. In the universe, there's lots of different types of electromagnetic radiation, otherwise known as light. It goes from types that have very long wavelengths, and it's a continuum, to medium-sized wavelengths, all the way to very, very short wavelengths. There's a bunch of different types of light, okay? And it's really just a continuum. It goes from very long to very, very short, okay? And scientists like to give names to things. So when we talk about the electromagnetic spectrum, we're basically just acknowledging that there is a continuum of types of light, otherwise known as electromagnetic radiation. I'll just do EM, electromagnetic radiation in the universe, based on wavelengths, okay? So really, like I said, there's long wavelengths, there's medium wavelengths, there's short. So you can kind of think about it like this. I'll draw this. The book doesn't draw it like this, but I think it's kind of good too. There's long wavelength light, and there's other types of light that have shorter wavelengths, shorter wavelengths, shorter wavelengths, shorter wavelengths, shorter wavelengths, and then all the way to super short wavelengths. Okay, so before we even draw and start labeling the different types of light or how scientists kind of qualify the different types of light, let's go ahead and put some other things on our chart here. Like I said, this side of the chart has long wavelengths. Long wavelength light, and this side of the chart would have short wavelengths. If you're thinking mathematically, this would be bigger numbers, and this would be smaller numbers, okay? Now, what we learned is that the longer your wavelength, the lower your energy. So this is also low energy types of radiation or light, whereas this is high energy light. So it depends on what you're trying to describe about it, but I like to put all of this on the same board. And let's also include frequency, this concept of frequency. Which side of this board is the, let's say, higher frequency side, higher frequency? Hopefully you see it, that it's this side, because this is the one with the really short wavelength, so you're going to get a lot of cycles. So this is high frequency light or radiation, and this is low frequency light. All right, so now with this on the board, let's go ahead and start labeling the different types of light. So in the universe, the light that's really long wavelengths, low energy, low frequency, this is what scientists deem radio waves. Now, the actual numbers, where the border is, where scientists kind of draw the line, is not important for us to know. There are actual numbers on this chart. You can see the radio wave goes to about 10 to the minus 1, which is the same as 0.1 meters of wavelength. But it's not really essential that we know the border. Just know that the longest wavelength light is the radio wave. Radio waves. Whoops. And then when you start talking about light that's a little bit shorter in its wavelength, these are what we call microwaves. And these are the ones that we use for AM/FM radio. These are the ones that are used in microwave cooking. So it's nothing different than what you're guessing here. When you move to a little bit shorter wavelengths, you're now talking about something called infrared. You've heard of this before. Infrared. And usually people talk, technically all of this can be considered radiation, but usually when we're talking about infrared, they use the word infrared light. Infrared light. So there's like a vernacular to it. These are also considered, it is radiation, but they use waves, microwaves, radio waves. In this section, you start using the term light, infrared light. And then if you go to a little shorter in your wavelengths, well, a lot shorter actually, but just on the spectrum, this is where you get what's called visible light. And visible light is the type of light, let me kind of draw this out here, that you are getting from light bulbs, that you're getting from the sun, okay, that allows us to see. In the visible light range, like I said, the different wavelengths have different colors, and the longest wavelength is red. And I would like you to know the order, because it actually does, you know, chemists do know things like this, because it relates to spectrophotometry and things like that. Roy G. Biv is the color, the different colors according to their wavelength. So red is the longest wavelength, then orange, then yellow. And it does correspond to like how you would draw a rainbow. The top of the rainbow is red, then orange, then yellow, etc. The lowest part of a rainbow is violet, and I is indigo, blue, and green. All right, so that's visible light. Now this is kind of interesting here. Why is it called infrared? Infra being kind of lower than. If you see here, it's right next to the red. So if you're a little lower than red, you're called infrared light. Now, what if you're a little kind of higher on the scale than violet? This is called ultraviolet light. So hopefully you see that these are not just like random kind of words. It makes sense. Ultraviolet light, sometimes people will call it ultraviolet radiation. This is the one that's, you know, causes skin cancer and is really bad coming from the sun. By the way, this is the one that they use for like night vision, like in the army, just so you can see like there's different applications to all these different types of radiation. After ultraviolet light, as you're getting shorter and shorter in your wavelengths, these are now called X-rays. X-ray radiation. And yeah, you're going to start to see the term radiation used preferably. Really, as you go higher in energy along this whole spectrum, you are increasing in danger. And what do we mean? In danger to what? In danger to your biological molecules. Visible light doesn't cause cancer. Ultraviolet light does. X-rays can be very damaging. We use them, you know, when it's better than not using them for like dental work and stuff, but they're not safe. That's why you put that lead thing on. And then, I think it's lead. And then the last type of radiation, gamma radiation. And this is the one that is released from like atomic bombs. Very dangerous, but also can be used for good. This is the type of radiation that they use in cancer treatment. Say if you have thyroid cancer, they'll use like a radioactive iodine to target your cancerous cells and kill them. So it's dangerous to the cancer cells. It's better to not use it than to just let the cancer go. But that's the idea, is that as you're increasing in energy, you're becoming more and more powerful in terms of what you can do to biological molecules and that type of thing. So I would like you to know the general order of the electromagnetic spectrum. All right, so let's go ahead and now talk about the wave nature of light. So now getting into how do we actually know that light is a wave? Kind of speaking on it very dogmatically as if we know. So what right do we have to say that light is a wave? It's not exactly something that you can just visualize and see. Here's the proof. And it takes a little while to develop, but let's go ahead and go for it here. So here is the experimental proof that light is a wave. This is kind of this next section here. So here's the key point, kind of the foundation to this whole thing here. All waves, whether they are water waves, sound waves, any physics phenomenon that physicists can call a wave. Remember, it's just more of a general term. It's not just about light. All waves display two really important behaviors. Display two behaviors. Or characteristics, I guess you could say. All right, what are they? The first is called interference. And the second is called diffraction. Interference and diffraction. So let's talk about what these two behaviors are, and then we're going to show you the experiment that proves that light does these exact same things. So therefore, if this is something waves do, and light does it also, light must be a wave. That's kind of the logic that scientists are using here. Okay, let's talk interference. By definition, interference is this. When two waves overlap in space, they either add up or cancel out. Okay, so let's go ahead and describe what that's all about here. So the first type is the adding up type of interference, and this is called constructive interference. Constructive, like you're constructing something. Constructive interference. Okay, let me go ahead and draw what's happening with constructive interference. Constructive interference, because you're building something. This is when you're adding two waves together. Say you have a wave, say this is one wave, and say it's like tilted this way, because you know waves can be faced in all different directions. All right, so say it's kind of headed south east. All right, and you have another wave that's headed northeast. Okay, eventually these two waves are going to enter the same space. If you can picture it, they were not in the same space originally, but eventually these two that I've drawn are going to overlap in space, just enter the same space. Now the way that I've drawn it is where these two waves are what's called in phase. These two waves are in phase. In phase. And in phase essentially just means that where one of them is experiencing a crest, the other one is also experiencing a crest. And then they both experience a trough, and then they both experience a crest, and then they both experience a trough. When they hit each other, they're going to be what's called in phase. And when they do that, they will add up. And add up means that they will essentially double their amplitude. Their wavelength will stay the same, but they're going to double their amplitude, his plus his. And so you can see it ends up to be a very large wave. Large meaning in terms of amplitude. Now, how will that be evidenced? Remember, amplitude relates to brightness. So this would be what you first had is kind of medium bright light. When these interact constructively, this will be very bright light because you essentially doubled the amplitude because of the way that they interfered. That's constructive interference. Destructive interference is the opposite. Destructive. So I'll keep my first wave, but I gotta change my second wave. With destructive interference, you're gonna also have two waves that are headed towards each other. However, I'm gonna draw these ones out of phase. So you can see with these two, where one is experiencing a crest, the other one is experiencing a trough, and these are called out of phase. When two waves that are out of phase approach each other, okay, you can see as they're totally out of phase, they will destructively interfere, and essentially they will cancel each other out. So I've just drawn a midline here, but no wave. They're just going to cancel each other out. This happens with water. Any kind of waves that physicists can study do interfere this exact same way. And what you will see here is darkness. The light will basically cancel each other out. So that's what we call interference. And now moving on to diffraction. What is diffraction? It's another behavior of waves. Diffraction by definition is this. When a wave encounters an opening with a size comparable to its wavelength, it bends around it. So bends being kind of like the key word here. So when you think diffraction, just think bends. So let's talk about what diffraction is. Let me go ahead and draw it over here. When you think about diffraction, you want to think about some kind of a barrier, like a wall where light cannot go through. But in order to see diffraction, you've got to have an opening in the wall. So that's what I've tried to draw here, an opening. Now, if you look at it here, it says with a size comparable to its wavelength. That's not just random words. That's significant. Let me go ahead and show you what I mean by this. If you have a wavelength, a wave whose wavelength is really much smaller than the opening, that's what I'm trying to draw here, you're not going to get diffraction. The wave's just going to go right through. There's not going to be any diffraction that happens. Similarly, and this is actually somewhat common sense, so if it feels easy to understand that makes perfect sense. Similarly, if you have a wave with a much bigger wavelength than your opening, you're also not going to get diffraction. It's just not going to go through because your opening is too small. However, if your opening has a size comparable in the same world as the wavelength of your wave, you are going to get diffraction. So let me go ahead and see if I can draw a wavelength somewhat, you know, comparable in size to this. This time, I'm just going to make it hit right here. You will bend around it. Okay, now I made mine bend down, but you'll get all sorts of bending. You'll bend up, you'll bend a little bit, big angles, small angles. There's going to be all sorts depending on how you hit that opening. So that's what is meant by diffraction. If you have an opening, you're going to bend through it. All right, so now putting this all together, it really is a beautiful, concise story if you kind of follow it all the way through. Now let's go ahead and talk about this experimental proof thing, because I've laid the groundwork, and now it's time to prove it. And there is a slide in your book that I'm going to be, let's see here, I'm going to be recreating it on the board. It's figure 7.7, looks like this. But I like it so much, I always do this. I always teach this because I think this is a cool experiment. Let's go ahead and talk about the experimental proof that light is a wave. It's really neat. So this is how the experiment was done. I'm not sure what the year was, but someone proved it at some point. So we have a barrier, but this time the scientists haven't put 2 slits in the barrier, and that is important to understand this experiment. We have a barrier, some kind of a wall that light cannot go through, but you have some openings, 2 openings to be specific. And on the other side of this wall, you've got some film. Just picture like camera film. So you've got some film. Okay, and picture, I'm not exactly how it was done, but picture that you're in a dark room and you've got some kind of a light source. So let me just write light source here. This is a light source. I mean, it wasn't a flashlight, but you can just pretend that it was a flashlight to understand the concept. Some kind of a light source. So light source is giving off light, and you're in a dark room. Okay, so we're thinking about light from the point of view that it's a wave. So let's go ahead and draw some waves here. So that light is providing, the light source is giving off light, so it's going to be kind of emitting light waves. So let me go ahead and start drawing some waves. So, I mean, obviously there's millions of them. I'm just going to be able to draw, I'm just going to draw 2, the ones that kind of, I'm going to illustrate the point. So you've got this one wave, and when it hits the barrier, it's going to diffract around it. And I'm just, for the sake of my drawing, going to have this one diffract down. And then this one here, I'm also going to draw a wave coming out. But when this one hits the barrier, I'm going to have him diffract up. Okay? So, and this happened trillions of times over, but I just, for the sake of the drawing, just draw 2 of them. Okay, now, when these 2 light waves hit their barriers, there's diffraction occurring. Diffraction, both places. Right there and right there. But because they diffract, they will now, instead of just headed straight, they're going to actually bend towards each other. And now we have what's called interference happening. Interference. So that's diffraction and that's interference. Now, the way that I've drawn it, are these waves in phase or out of phase? Right here, where they interact, this one is experiencing a trough. This one's experiencing a crest. So that means they are out of phase. And that means these 2 waves are going to cancel each other out. And when they hit that film, you're going to see darkness. However, if I had drawn 2 other waves just by chance, you would get other waves that were happen to constructively interfere, and you would get brightness. And that would happen over and over again in a pattern form. And what you would see is something called, a very famous thing called an interference pattern. This is called an interference pattern. And that's exactly what scientists saw when they did this type of experiment, the interference pattern. So here is the beauty of it all. Scientist runs an experiment. They have a light source. They let the light approach the 2 slits. they can't see any of this happening. This is all just our best understanding. What they see is this. This is the data. This is the evidence. Black, white, black, white, black, white. The reality is they have to explain it somehow. How did we go from 2 slits to this zebra-like pattern? And the idea here is it is only explained, as far as we've been able to tell, from diffraction and subsequent interference in a pattern-like way, where you get destructive, constructive, destructive, constructive, destructive, destructive, constructive. And once again, this is the evidence that the only explanation for this is these wave behaviors, and that is the proof that light is a wave, because we have no other explanation for this behavior. And so with that, we conclude light is a wave. Now, what we're going to do here is end this video, and then the next video is going to talk about, okay, hold up, light is also sometimes best considered a particle, which is what we call a photon. So in other contexts, light does not act like a wave, and it acts much more like a particle. That is Albert Einstein's major contribution. And we're probably not going to spend as much time on that as we usually do. I'm going to, just because of the remote learning aspect that's going on this semester. However, we're going to lay that groundwork, and then we're going to understand that everything that we've been learning about light, this whole, yes, it's a wave, yes, it's a particle. Once we start to see some similar things happening with electrons, yes, it's a wave, yes, it's a particle. Scientists took that, ran with it, and came up with this new theory called quantum mechanical theory, or quantum mechanical model of an atom, which leads us to orbitals, s, p, d, and f orbitals. And frankly, in the coolest way possible, which I will try my very best to help you understand how cool this is, completely explains the entire structure of the periodic table. Actually, not just the structure, but the existence of the periodic table. Remember, the periodic table is not something that was designed by humans. It was discovered by humans. The periodic table has always been since the creation of the elements. And the structure of it, the idea that you can have a table, the idea that it dips down in this area, the idea that you've got these 2 rows at the bottom, it's all related to orbitals, to quantum mechanical theory. Very, very cool, kind of completing the circle that happens with chemistry. So hopefully that gives you a little window into where we're going with this chapter, but this is where we should end for this video. Thank you for your attention. Light is a wave.